and welcome everyone. We are talking about half-life today, but before we talk about half-life, I'm going to give you a little bit of nuclear and radioactive decay, okay? So, I don't know if you've ever recognized this, but on your periodic table, there is this entire section right here that says Table of Selected Radioactive Isotopes, okay? So, I'm going to talk about this for a second here. Elements are stable for the most part until we reach about element number 83. After element number 83, that's where we typically say that now these nuclei are going to decay. Remember, for a regular chemical reaction, all that happens is your electrons are being exchanged. They share electrons, they lose electrons, they gain electrons. Well, or you can switch elements, right? So, it'll be carbon with oxygen and then it switches to carbon and hydrogen, for example. But what happens here is this is where in nuclear chemistry where we actually alter the nucleus, okay? And so there are basically about 5 different modes of decay that we can talk about. So, and I'm not talking about like fusion and fission here, but specifically losing particles where your nucleus ends up decaying and then different particles are given off and you end up with a new element, okay? So over here, if I kind of zoom in on this, this is a table of radioactive isotopes. And over on the side here, it gives us this little key that talks about the fact that these are half-lives and they can be in seconds, minutes, hours, or days. And so we can see alpha emission, beta particle, positron, and so on. So let's take a look, for example, at the isotopes of carbon. Now, these are selected isotopes, so there are other isotopes that exist. But carbon-11, for example, has a half-life of 20.4 minutes, and it goes through what is called positron decay, or beta plus, whereas carbon-14 has a half-life of 5,730 years, and that goes through beta decay. So it depends on the isotopes, because sometimes people will say, carbon is radioactive. Well, what isotope are you talking about? Or carbon has a really long half-life. What isotope are we talking about? Okay, so that makes a difference. All right, so I want to show you, before we kind of move on, this, what is called this belt of stability, okay? The belt is not the red line. The belt is actually this blue line. And this blue, these dots, all these dots, represent the elements that are more stable, okay? And the elements outside of that are going to try to decay until they reach the line. And so they will form new elements, and their nucleus will actually separate and break apart until, or sometimes they capture things in order for them to get closer and closer to this belt of stability. This red line here is showing a 1-to-1 ratio. This here is a, here it is, 1-to-1 neutron to proton ratio. So if we look at our axes, this is number of neutrons and this is number of protons that we're looking at. And so we know the protons are the atomic number. So when we look at this, we can see that right up to about element number 20, right here, is where the 1-to-1 kind of matches. What does that mean? Well, that means that those are pretty much stable when they have 1 proton to every 1 neutron. Let's take a look back at the periodic table to see if we can figure out what this means. Well, here's element 20, calcium. And look at this. We know that this is the atomic number, which is the protons, and this is the mass, which is 40. Now, yes, it's the average, but that's where we have our most stable different isotopes, right? Well, that means that it has 20 neutrons, because remember, you subtract to get 40 minus 20 to get how many neutrons you have. And if we look at something like magnesium, we're at like 24, and 24 minus 12 is 12. So for 12 protons, we have 12 neutrons. But if we look at something like, I don't know, maybe we look at something like tin right here. We've got 50 protons, but it says it's 118 is the mass number. So if you subtract that, then we're looking at a solid like 118, right? Minus our 50, we're looking at a way more than 50 on here. So the nucleus is actually able to accommodate a lot more neutrons as we increase, okay? And those can still be stable. So until we get to about element number 83, and we can take a look here at the belt, we can see that here, if I were to kind of like go from like 83 and kind of take this up, I can see that that's basically where my belt ends, is right here at like bismuth, okay? And so that's where the belt of stability ends. And so just to kind of give you a little bit of heads up, and this is kind of cool to know, The elements will actually decay according to radioactively decay, go through a radioactive decay, according to the first order rate law, okay? So these elements typically will decay according to first order, okay? So let's come down and I wanted to show you a little bit too of like some decay modes and what is half-life. So we know that the half-life is simply the time it takes for half of it to be gone, okay? So that's all that half-life is. It's pretty easy. So if you start off with 100 grams of something, after one half-life, so this is just showing half-lives, but every half-life is about 5.3 years, they're saying. So like this will be about 5.3 years here. This is going to be about after about 10.6 years and so on. Well, what happens is half of it is gone, and so now we have 50. The misconception that people will have is, well, after another 5.3 years, I have 0, because I started with 100 and it went to 50, and now if I subtract another 50, I'm going to get 0. Wrong. You have to divide it by 2 again. Okay, so every half-life, it divides by 2. So every half-life, I'm going to say divided by 2. Another half-life, divided by 2. Another half-life, divided by 2. So then, if I said we're starting with 10 grams and it's going to go through 3 half-lives, how much do I have left? So what I would do is I would say 10 divided by 2, divided by 2, divided by 2, not divided by 3, okay? So it's 3 half-lives, but that means it's going to divide by 2 3 times. I hit equals, and I get 1.25 as my answer, which is exactly what we said it should be after it goes through 1, 2, 3 half-lives, okay? But here's the situation. Sometimes they don't give you an exact number. They don't say 3 half-lives, and maybe they say, so 5.27 times 3, maybe they say after 15.81 years, and you're like, oh, 15.81 divided by, that's 3 half-lives, then you could figure it out that way. But maybe they don't give you an exact number. They might give you a number like 17.5 years or 11.2 years, something random, okay? And so it's not as easy to do. And so there's an equation, of course, that we can use, okay? And so this is showing cobalt-60, which is this example. It's actually used to irradiate bacteria on food, and this happens quite often. It's called food irradiation. A lot of people don't even know that their food is being irradiated, and so that's what they use for that. This is showing bismuth. Same idea here. We can see that the half-life, every half-life is 5 days. So if I said I'm starting off, let's start with, maybe we start with 50 grams instead, and I want to know after 2 half-lives how much I have. So again, what I would do is I would say 50 divided by 2 and hit equals, and I get 12.5. So again, it would be divided by 2, and I get the 12.5 after 2 half-lives, okay? And so if you know how many days it is, you could figure out your number of half-lives. And so let's take a look at the equation, because the equation is really nice to use, okay? This equation is not given to you on the AP equation sheet. I do think it's a very helpful equation, and in the past I've told students that it is a good idea to just memorize it, so it is really helpful. So, and I usually, this is a nice way to memorize it. A equals A 0.5 to the T over T 1/2. Or what a lot of people will do is they will use A over A 0. So you have your starting amount is underneath, your ending amount is on top, which means you're going to get a fraction, okay? It's going to be a fraction. This number will never, ever, ever be bigger than 1, okay? So I always want you to remember that, because your starting amount has to be bigger than your ending amount, okay? So this is A, or A final, or A at some time, okay? So sometimes they'll even call this A T, for example, okay? Then it's easy to remember too, because you can say it's A2, all right? Is equal to 0.5 raised to the T over T 1/2. Okay, so let's label these. So what is A? A is actually my final amount, and you can do this, usually it's in grams, okay, almost always in grams, sometimes it's in milligrams or something like that. A0 is your initial amount, and then T is the time that you let it decay, time to decay, so how long did you let go by, and T, capital T or T 1/2, is your half-life time. This is really important, okay, because I'm going to tell you something in just a second here. So both of these should have units of, let's say, grams, okay, and I'm not going to put parentheses there, grams, and both of these should have units of, let's say, seconds or minutes or something like that, but you need to make sure, you need to make sure that your unit is the same, okay? It's really important that we not only understand what AT, A0, T, and T1/2 represent, but what happens when you divide AT by A0. So if you know the amount in the end, and you know your starting amount, and you divide those two out, what is that telling you? What is that fraction representing? Are you thinking this is actually the fraction that remains? This is if, for example, and by the way, if I told you 60% of it decayed, well then 40% remains. So I could call that 0.40, okay? And so that's what that fraction actually tells us. Now, what about T over T1/2? Well, if I know that my total time, let's come back up to this example here, my total time is 15, let's say it's 15 days that I'm letting it decay, okay? And I know that every half-life is 5 days. Well, if I do 15, my T, divided by my half-life time, which is 5, that gives me 3. And what is that 3 representing? Well, 3 is representing that over 15 days, it would be going through 3 half-lives. So, you guys, this is really, really important. These have units, both of them have units of seconds or minutes, But both of these together represents the number of half-lives, okay? And so this does not have a unit. And same thing when we talk about a fraction has no unit versus these are both, let's say, in grams or milligrams or something like that, okay? So just making sure, because even though it looks like 4 variables here, you could have a problem where it's just representing 2 variables. If they give you the percentage or they give you the fraction that remains or like decays and you do the opposite, and then they give you the number of half-lives, then that's all you need, because students will be like, wait a minute, why are they only giving me 2 variables? I'm trying to use the equation. I think I'm supposed to have 4, okay? Now, the only other thing with this equation is there is a little bit of a twist, and so I'm going to come to that because a lot of you probably have done this in your math class, but you've forgotten. What if your exponent is x, okay? What if your exponent is x? And so that's kind of something that we need to make sure that we go over, so hopefully this ends up helping you with your math class as well, okay? So let's take a look at a pretty simple problem here. Actually, I'm going to come back to these problems. I have an extra page, and so let's take a look at some of the problems here. This question says, how much of a 135 gram sample of cobalt-60 is left after 15 years if the half-life is 5.271 years? Okay, it's a lot going on here. So underline the numbers that you know, and what are we looking for? So we want to know how much is left. How much is left? So we're looking for the final amount, okay? Which means I know I'm looking for AT, okay? The amount final after a certain amount of time has gone by, all right? So 135, well, that must be my initial amount. That's my A0, okay? 15 years, oh, that's easy. That's my time. So what's 5.271? Well, that tells me that it's my half-life time. Before we even do this, let's see if we can conceptualize it and get an approximate answer. So we're looking for how much is left, and they're telling us that it's 15 years, and the half-life is 5.271 years, which is about 5 years. Well, how many half-lives has it gone through? Well, about 5 years. And so if I do 5 times 3, I get 15. That means it should go through 3 half-lives. So what I'm going to do is I'm going to take my 135. This is kind of like a little bit of a side note, but I'm going to take my 135. I'm going to divide it by 2, divide it by 2, and divide it by 2, and let's see what we get. So 135 divided by 2, divided by 2, divided by 2, and I'm getting about 16.875 as my answer to this. So now this is approximate, right? So I'm just going to say it's about 17, and we're in grams, so it's going to be about 17 grams. So let's see what our answer is when we actually do the calculation, okay? So I'm going to write, now because I know I'm solving for AT, I am going to actually write this where I do A equals A0 times 0.5 to the T over T1/2. And let's fill in our values. So because I'm looking for AT, I'm going to leave that on that side. I just multiplied A0 to the other side. So my A0 is 135 grams, and then I'm going to multiply that by 0.5 raised to the t, which is 15 years, divided by my t1/2, which is 5.271. And if I work this math out, so go ahead and plug this into your calculator. Make sure that you do 0.5. You can do 0.5 caret and then put parentheses for the 15 over 5.271, and let's see if you get the same answer I get. Okay, did you get 18.8 grams? And by the way, the years cancel out here with the years here. So those cancel out, and I'm simply left with grams. And so 18.8 is pretty close to 17, right? We approximated it because it wasn't a half-life of 5 years. It was a 5.2, but just to approximate and be able to get that answer, okay? So this next question says that we want to know how much they had 30 days ago. Okay, so we're actually looking for, so it says how much did they have 30 days ago, which means we're actually looking for the original amount. We're looking for A0 now, okay? So what you can do is you can algebraically solve for A0 if you want in the beginning. So if I do that, that means that I'm looking for, so if my equation is A equals A0 times 0.5 to the t over t1/2, then what I want is I want this. So what I'm going to do is I'm actually going to get this divided over to the other side. So I'm going to move all of this over to the other side over here, okay? So let's fill in the equation. So do I know how much I have left? Well, it says after they inventoried, they have 26.3 grams of it left. That's my A at the end after a certain amount of time. So that's my 26.3 grams. I'm going to divide it by 0.5 raised to the t over t1/2. What's my time? Well, it says 30 days, so after 30 days have gone by, so 30 days divided by my half-life time, which is 17 days. Again, my days are going to cancel out. So go ahead and plug this into your calculator, and let's see if you get the same answer that I do. And did you get 89.4 grams? So A0 is 89.4 grams. You could do a quick check of your answer again, okay? I'm going to estimate that this is about 90 grams or so, and I can see that if it's 30 days ago and every half-life is 17 days, then one half-life is 17, a second one will be 34 days, but we're about 30 days. So it's about 2 half-lives roughly. So if I do about 90 divided by 2 and divided by 2 again, I'm getting around 23 grams. And we know we started with 26, so I'm close, okay? Again, because we just want to make sure that we're estimating this too. All right, so now what happens is, what if instead we're actually looking for the exponents, okay? We're looking for one of the exponents, which means I'm either looking for t or t1/2 or t over t1/2, okay? If that's the case, you have to throw in the log. And here's my analogy, okay? So my analogy is that when you throw in the log, the exponent drops in front of the log, okay? So you take the ant and you drop it in front of the log. And so then what you can do is, once it's in front of the log, and then you use your log key. But remember, in algebra, what you do to one side, you must do to the other side. So if you're going to take the log of one side, you have to take the log of the other side. And so remember, all log is its base 10, okay? And so it basically gets rid of that exponent, and it turns it into just a number or an integer or maybe a fraction in this situation. So let's just go right into it and see how this works out. So for example, this question says, we're going to do one of these in the notes. So I'm going to come right back to this. Let's take a look at this one right here. So this iodine question. And by the way, what iodine is used for, one of the popular uses more recently was in Japan when they had a nuclear fallout. If you're exposed to radiation, they can administer potassium iodide, and what it does is it blocks the thyroid from absorbing more radiation. So iodine 131, though, is a radioactive isotope, and so it's used to test how well the thyroid gland is functioning. So they're asking us how much time has passed, so we're looking for T, for a 700-gram sample, so to decay. I always want to look to see, like, what's my A, T, and what's my A0? Remember what I told you? I said that A0 has to be a bigger number. So this is the original amount because you can't end with more than what you started with. It's decaying, okay? And so this must be my AT, all right? So if we go ahead and we fill in our equation, so I'm going to use the AT over A0 equals 0.5 to the T over T 1/2. And the question is, what am I solving for? Okay. So I know I'm looking for how much time has passed. So I know that I'm looking for T. Okay. Oh, and by the way, this is 8.04 days. This is representing my T 1/2. So this is representing my T 1/2 or my half-life time. It says the half-life is 8.04 days, okay? So let's fill in our numbers here. So AT is 43.75 grams. And then I'm going to divide that by A0, which is 700 grams. And that's going to give me my fraction remaining. That's going to tell me what is left, okay? What remains, not what decays. It tells me what's left, is equal to 0.5 raised to the T, which is what I'm solving for, divided by 8.04 days. Okay, so I'm trying to solve for something in my exponent. So here we go. Here's what we're going to do. We're going to throw the log in, and when I throw the log in, the ants or the exponent is going to jump in front of the log because he's like, the log is coming, okay? So it jumps in front of the log. So watch what happens here, okay? Oh, let's just divide this out real quick. So we've got 43.75 divided by 700. It gives me 0.0625, okay? So what I'm going to do is I'm going to throw the log into both sides, which means I'm going to throw in, let me just do this in a different color. I'm going to throw in the log of this number right here is equal to the log of, and now what happens is I'm going to put the fraction in front of this, in front of the log, okay? So leave a little bit of space. I'm actually going to undo this. I'm going to leave a little bit of space for my fraction. And so I'm going to say the log of 0.5, but this entire fraction, this is my ant, this is my exponent. It's going to come right here, and I'm going to have T over 8.04 days, okay? Now I need to solve for T, okay? I need to solve for T. So how do I do that? Cross multiply, everybody, okay? Cross multiply and divide. If I want T alone, what I'm going to do is I'm going to cross multiply by 8.04, but since it's being multiplied by log of 0.5, I'm going to divide by it. What am I entering into my calculator? I want T alone, so I'm going to start on this side, and I'm going to type in my calculator, log of 0.0625 times 8.04. Then I know I need to divide by the log of 0.5 because I want to get rid of that. Go ahead and plug this into your calculator, and let's see what you get. Did you get that T is equal to 32.2, and this is in days because that my 8.04 was in days, so this must also be in days. Did you get that answer? Okay, hopefully you got that. So this question, next question is asking for half-life, which means now I'm actually solving for T 1/2 instead, but it works exactly the same way, okay? So I just wanted to kind of give you a little bit of an idea of that. And the last thing, as far as like before we go back and do the half-life problems and fill in the notes is, I wanted to make sure that you're aware of carbon-14 dating because this does actually come up. So what happens is we have a certain amount of carbon-12 and carbon-14 in our bodies. All living organisms do, okay? And so while we're alive, it remains pretty much constant, okay? After death, and so we can think of like a tree or a plant or like whatever it is, then it'll decay and the carbon-14 to carbon-12 ratio decreases because the amount of carbon-14 actually starts decaying, but the carbon-12 remains constant. It doesn't change. So after things die, only carbon-14 changes. And so if we can compare the carbon-14 ratio to the carbon-12 ratio, we can actually figure out how old something is. And so it's pretty cool how that ends up working. So for example, this question right here is talking about like a papyrus plant, and they're trying to age the papyrus to see how old it is. And so it says, if the scroll is 75% of what it was before, well, what that's representing is that's representing our amount that we have remaining. That's our AT. They're saying that 75% is what we have left of it, okay? And so what we can do is we can basically just say that that's 0.75 is my fraction remaining. So if I have AT over A0 is equal to, so AT over A0 is equal to 0.5 to the T over T1 half, then what I know is this entire fraction is 0.75 or 75%. Okay, or you can say it's 75 over 100. Okay, so you can use numbers to fill that in. Is equal to 0.5. Now, what we know is we know that the half-life is 5,730 years. So I know I'm looking for T, I'm looking for how old it is, I'm looking for the age of it, and I can divide that by 5,730 years. Now again, what do I need to do? I need to throw in the log, okay? So I'm going to throw the log into both sides. So I'm going to do the log of 0.75 is equal to, remember, leave a little bit of space, the log of 0.5, but then here I'm going to do T over 5,730 years. Same thing as last time. All I'm going to do is I'm going to solve for T. So in my calculator, I am going to do the log of 0.75 times, cross multiply, 5,730 divided by, to get rid of the log of 0.5, divided by the log of 0.5. And so then when I do this calculation, I end up figuring out how old it is, and I end up getting 2,380 is how old it is. 2,380 years is how old my papyrus plant is. And so that's called carbon-14 dating. That's kind of the method of like how they end up figuring it out. And so literally like there will be holes in it because what happens is carbon-14 goes through a mode of decay that is called beta decay. And when it goes through beta decay, it actually will turn into carbon-12. So carbon-14 will turn into carbon-12, and carbon-12 is a gas, and so you actually can't see it. So there will actually be holes in the paper. So it's kind of cool to be able to get an understanding of what happens with that. Okay. All right. Come back to Q5, and Q5 says a sample contains 100 grams of some substance, and after 16 days, so this after 16 days, it contains 63.1. I always like to check to make sure. Remember, my initial has to be bigger than my final. So this must be my initial, and this must be my final, my AT, and then 16 days would be representing my T. So in this case, all I'm going to do again is I'm going to AT over A0 is equal to 0.5 raised to the T over T1 half. And so if you want to try this out again just to see, I know I am solving for my T1 half. So let's figure this out because this is a little bit different. So I've got my AT is 63.1 grams divided by 100 grams, and that's equal to 0.5 raised to the T, which is 16 or 16.0 days, divided by X. So I can just call it X, or I can call it T1 half, and this is what I'm looking for, okay? All right, so let's see how you do. Go ahead and see if you can solve this with your log, and let's come back and see what we have filled out. This one's a little bit different here, right? So what happens here is my unknown is in my denominator. So what I'm going to do is I'm going to use my swap thing here. And by the way, if you got the answer around 24, you got it, okay? And so what I'm going to do is I'm going to swap these out with each other. And when I do that, in my calculator, I am going to type, so if I switch these with each other, I'm actually going to do 16 times the log of 0.5, but then I'm going to divide by the log of 0.631, and when you do this, you should get that your T1 half, your half-life time, is equal to 24.1 days. Okay? All right, so people will say things like, okay, but I can do this, that, and the other thing in my calculator. Then you should be able to do this too. If you're smart, you do not need your calculator for your functions, like special calculators for functions. If you're smart enough and you're in an upper level math class, this should not be difficult. For not understanding it, do a quick little rewind and make sure and replay just to make sure that you have it down because it is really easy algebra, okay? None of it is very challenging. All right, so let's flip to the next page in the notes here. And this first question is asking us, it says that there's a first order reaction and it has a half-life of 20 minutes. So this is our T1 half, okay? and they're telling us it's first order. And so what I'm going to tell you is if it's first order and only if it's first order. So elements decaying are first order. And if they don't say anything to you, usually you can assume that it's first order. Okay, but if they ask you to figure it out first, you figure out it's second order, you cannot use this equation. Here it is, right here. For a first order reaction, it's 0.693 over K, okay? And that's what it's equal to. It's kind of a variation. If you actually type in your calculator the natural log of 2, you will get 0.693 as the answer. So it's kind of a variation of the ln of A equation. Remember that was for a first order, was ln of A versus time being linear. So it's that equation adjusted and then using ln of 2 because it's half, but then it's like the natural log of 2 when you algebraically move it over. And so if it's first order, you can use always A equals A0, 0.5 to the T over T 1/2, okay? But, an AT, right? And then you would solve for whatever it is that you're looking for. But there's no K in this equation, so that's not helpful to me. On the equation sheet, if we do take a look at the AP equation sheet, what we will see is that down here under the kinetic section, the only half-life, like relating half-life to K equation that they give us is for a first order. They don't label it, so this is our first order rate law, this is our second order rate law, and then they give us the half-life for a first order, but they don't give us the half-life for a second order, which usually means that they're probably not going to ask you for it on the test, but I will be asking you because you will have the equations, so just in case you see questions like that. So this is just asking us to calculate K using this equation. Well, if I'm calculating K, the equation is T1/2 equals 693 over K. Swap thing, everybody. Swap those out with each other, okay? So I'm going to get K is equal to 0.693 over my half-life, which is 20 minutes. And so if we divide this out, we should get that the answer is 0.0347. So 0.0347. It's first order, which means it's my unit of K is simply equal to seconds to the -1. But wait, this isn't in seconds, it's in minutes. So that would be minutes to the -1, and that would be my units of my answer for K. All right, so if you know the half-life, it makes it really easy. Now watch this question. It says, how much time, looking for T, is required for this reaction to be 75% complete? Now what we're going to first do is we're going to think about it for a second, okay? So I know that it's 20 minutes is the half-life. So every 20 minutes, I know that half of it is gone. So if it's 70 minutes, 75% complete, then what we're thinking is, okay, after one half-life, then it's 50% complete. After a second half-life, it should be 75% complete, okay? So if that's the case, then I'm going to say after 20 minutes, let's kind of write this down, then 50% of it is gone. After another 20 minutes, then another 25%, which means 75% must be gone of it. So how long is that? Well, that's 40 minutes, okay? If you're like, my brain doesn't work that way, okay? It doesn't work that way. We're going to use an equation, okay? And so since we can, we're going to use our first order rate law equation. So what I'm going to do is I'm going to write my ln of A, and by the way, we can also use A equals A0 to figure this out. So just to kind of remind you of this, ln of A minus ln of A0 is equal to negative KT. And so I know I'm looking for T, I'm looking for time. So I'm going to fill this in. And my K, we actually just figured out, so we can divide by K once we have this down. So if it's 75% complete, something that's really easy to do is to maybe call it 1, and then if it's 75% complete, or 100, because some people like to use 100 instead, then how much is actually left? So I like to say it's almost like starting with 1, and then if it's 75% complete, then 0.25 is what we have basically left. Or you can say 125 is what's left, okay? So that means that my original amount, I could say is, my initial amount, I can say is 100, and then my final amount, I can say is 0.25, okay? So let's do that. So let's do the ln of 0.25 is what I have left minus the ln of what I had originally. I can just call 1 gram, for example. And then if you're okay with it, I'm going to divide the negative k over to the other side. So negative 0.0347, and again, that's minutes to the negative 1, and that should be equal to my t, okay? So go ahead and plug this into your calculator, and let's see what you get. Did you get that t is equal to 39.95? Well, that means that t is equal to 40 minutes. Hey, okay, now, let's check to see how a equals a0 would work out for this. And so all I would do, and I'm not going to show you the whole thing, but I'm going to do the at over a0 is equal to 0.5 to the t over t1/2. But just to kind of explain a little bit, because you can try it out too. But we know that we're looking for so in this case, we're looking for, we know our half-life time is 20 minutes. And so we know that we're looking for t, okay? And so all you're going to do is you're going to plug in your AT, which again, you could say that this is like, it's 75% complete. So that's how much is gone, which means 25% remains. So you could say 0.25 is equal to 0.5 raised to the, I know I'm looking for how long it takes, divided by 20 minutes. And so you can use the log and then be able to calculate what t is. And again, you would get that t is equal to 40, okay? So just another way of doing that. Okay, and last part, we already filled out this integrated second order rate law from the integrated rate law video, but we stopped when we got down to C. Okay, so this was a second order reaction, and what they were asking us to do was to calculate what the half-life was for this particular substance, for this C4H6. So that was like part C in the problem, was what is the half-life? Okay, so if it's first order, we would use this equation, but it's not. It's second order. So since it's second order, notice how the equation is different. It's not very different. It's t1/2 is equal to, instead of 0.693 over k, this is 1 over a0, also divided by k. So instead of 0.693 over k, remember 1 over a0, or the original amount, that was our equation when we were doing the second order rate law. So it was 1 over a minus 1 over a0 is equal to kt. Remember that one was positive? So it's similar to that. So let's just fill this in. So we know we're looking for the half-life. And so all I'm going to do is I'm going to do 1 divided by my original concentration. So I do have to take a look up here to see what my original concentration was. At time 0, it was 0.01 molar. So I'm going to do 0.0100 molar. And then I'm going to divide it by the K. We had already figured that out in part B over here. And we figured out that it was 0.0607. And so then all I'm going to do is divide these two numbers out. And when I divide that, I get 1647, or with sig figs, we get 1650. And this is a time, this is a half-life time. And so if we look at our units, it's going to be seconds, okay, since that unit is in seconds. And so that would be how long one half-life is, okay? I know it's a lot. Hopefully this is helpful to you. You got a little bit more information than you actually needed on half-life, but always nice to review some of that stuff that you would do in Honors Chem, okay? Happy day, everybody.